But once you work all through that, you'll get an approval. You'll get an approval, a formal letter from them saying that based as how you've described your plans, we'll agree to pay you X amount of money to offset the costs of whether it's IT or infrastructure related or general building related. And then you can either appeal it if you think it's worth more money, or you'll formally respond to them that you accept their offer. That is when, so after all that's done, so it's not until step 4 where you'll actually start your project, where you actually want to start your project, go out and buy your equipment, start the construction work, whatever it takes. But it's not until that point where you've gotten a formal agreement back and forth, that's when you want to actually take action. And so we've talked to some customers that have missed out because they had started taking action, because they thought it made business sense to do it anyway. They had started taking action, but because the utility hadn't approved it first, they really ran into a lot of headaches, and in a couple cases just didn't get the rebate at all. Because the utility company said, well, you're going to do it anyway. It made business sense for you. You don't need our help. So you don't want to fall into that category. And then the final part, the payout, there will be a verification that has to take place. So you've done your project, but then the utility will want to verify that what you've done was actually in accordance with the plan that was submitted and approved. So there's a verification and measurement process that'll go on afterwards. And then the checks are cut. So that's really how we look at it at a high level. So how do you identify what types of programs? Really, one of the things that I think some other vendors have done it too, and one of the things Eaton is working on is building a list of who are the right contacts within utilities and in all the different utilities, and trying to get that out to our customers to help them. And there are other ways to do it. There are certain websites you can go right to the utility, or there's other websites that are trying to build a business out of being kind of like a data aggregator. But there's a lot of information out there, and really the key is just to take that first step. And here's just some statistics from Data Center Knowledge that that I thought was interesting to throw up, just to show that when you talk about because now we're going to talk more about the infrastructure part of rebates. Power and cooling is still on the top of mind with a lot of data center managers today. A lot of it has to do with a lot of people have done their virtualization projects, so physical space isn't an issue as much as it is now. The densities maybe that they're running. They've got more. They're filling up power in their cooling capacity now more than their space because of the virtualization projects that they've done. Even data center design, I'm sure a portion of that's reliability, but I'm sure a part of that's also efficiency. So really there's a little bit in all the top categories that this efficiency thing is key interest to data center managers. This slide here, I'll talk about the importance of energy efficiency. Again, this slide is slanted towards mechanical systems. So this slide is based on a report that was done by Lawrence Berkeley National Labs a few years ago, and it studied 2 different data centers from 2000 to 2006. And you can't see the pie charts too well, but in facility 1 on the top, only 33% of the power going into the building was being used by the IT equipment. On the slide on the bottom, the circle on the pie chart on the bottom, 73% of the electricity was available for IT equipment. And the big difference was that green part in the top, which represents the mechanical systems, the HVAC, the chillers, the pumps, the crack units, was using all that energy in the first case, but in the bottom slide, it's the light blue on the top side. So basically, what people were able to save in the mechanical system went directly to the IT loads. And to make that into a more real-life example, you can see the numbers up there. If you assume a 200 kilowatt facility, just based on the percentages that were in that report, it's an annual savings of over $60,000. That's for a 200 kilowatt facility. Obviously, the bigger the facility, it'll be more savings. So let's talk a little bit about what factors contribute based on that last slide, right? Let's talk about what contributes to that type of inefficiency in a data center. Well, there's chaotic cooling practices. We're going to talk about that. Poor rack hygiene, which is something I think people understand but sometimes overlook because it's a small detail. And then a little bit about UPS systems and how that technology has come along over time. We'll talk about each one of those. So what is chaos cooling? So what do I mean by that? Well, really, I was surprised to find out, living in the data center world every day, you talk to a lot of thought leaders, and I was actually surprised to find out that, maybe only 80% of data centers today, and I could be off on the percentage, but it's around there, actually even use hot aisle, cold aisle. That some data centers out there today still don't even use that. When you come to a lot of these conferences, you think it's just common practice, but apparently it's not. But the chaos cooling is just more or less, you typically will have a raised floor. You're trying to flood the room with cold air, and you're hoping, and sometimes it's a hope, that the cold air is getting to the equipment where it needs to be, and that the hot air is being sent directly back to the crack unit or to an exhaust system where it's not staying in the data center. I think people over time have realized that that's not always what happens. So and as densities get higher, right? So this type of cooling works very well if you're, different people tell you different numbers, but anywhere 2-3 kilowatts per rack, this type of, or under, this type of cooling system will work okay. Once you start getting above that, this type of cooling system breaks down pretty rapidly. So what are some of the three, so here's a list of the three main types of problems that occur with this chaos cooling. If you get the recirculation, with the recirculation is basically when the servers are drinking their own exhaust, right? And this will typically happen either at the hot air from the hot, the back of the rack is either coming over the top, typically that's what happens, or if it's at the end of a row, might come around the side. But in either case, what happens is there's not enough air coming up from the cold air coming up from the floor. The server fans are still need to draw in air, because they're still moving. So they'll take what's available, and that's typically hotter air. And it's been pretty well documented over time that the servers at the top of a rack have a higher failure rate than servers at the back of the rack, and this is one of the leading causes, this recirculation. Air stratification is another problem. And that's natural, right? That's, heat rises, right? So in this room, the temperature, the ceiling is going to be a little bit less potentially than the temperature at the floor. That's just a natural impact of thermodynamics. That the heat's going to rise, and the temperatures are going to just fall that way. Bypass here, so a little bit has to do with we talked about rack hygiene, but it's basically when you have the hot air mixing in directly with the cold air stream and going back where, and what happens is sometimes in order to fight that, people will change the set points or the fan power on their crack units, which will pump more cold air under the floor. But as a result, the velocity of the air coming out from the floor tile, especially if the floor tile doesn't have enough open space, it'll shoot the air up faster, and sometimes that will just bypass the rack altogether and just shoot right back to the crack unit. And then the crack unit thinks the room is much colder than it really is, or at least what the servers are seeing, because it's the velocity is just too fast. So the cold air is not able to stop and go into the servers. The server fans can't pull it in. So these are the three types of things that can happen in a chaos cooling environment. So, over time, you can see here's a little timeline put in by Rightline, and you can kind of see how things have evolved over time. Early on in the early mid-90s, people would put fans, in the rack, like little muffin fans in the roof or in the back of the rack or on the front doors, just to try to assist to blow more air towards the servers. Back in the early 2000s was the Tower of Cool. That's a picture of the Tower of Cool, which was a design by by an engineering firm in Baltimore, holds the patent on that. And that was really one of the first systems that tried to separate the hot air and cold air specifically. And then really back as early as the mid-2000s is really when companies started to take a look at and we started to see different versions of heat containment systems, whether it was the chimneys on the back of the rack all the way up to aisle containment, a few years ago, where you were really putting the hot aisle or the cold aisle into a room. And those were the ways that, and they're very effective. We see more and more adoption of it, that you can separate that cold, you can keep the cold air in front of the servers, and you can take the hot air and bring it back to the crack units directly. Or nowadays, with people getting, there's a session on the ASHRAE guidelines, I think, this week, and a lot of people are moving away from crack units. They'll just move to the building style, building size, economized systems with either air side economizer, water side economizer. But we're starting to see people move away from even putting crack units. As the pressure is to lower the PUE, and based on those pie charts we saw before, people are trying to eliminate crack units altogether. And with the new ASHRAE guidelines, it's feasible to do so. So we wanted to show four temperatures that you want to keep in mind that'll indicate to you whether or not you have chaos cooling present in your data center. So the first, and really it's four temperatures, but two deltas that you want to measure. So the difference between the air coming out of the bottom of the crack unit, if that's what you have, or whatever cold air supply that you're using, and the air going into the server, right? The difference, if those two temperatures are different, there's losses. There's losses in how the cold air is being supplied to the servers. And likewise, the air temperature in the back of the rack compared to the temperature that the crack unit sees, right? You want them as close as possible to be the same. Otherwise, there's probably air mixing going on in a room. So four very easy temperatures to measure without getting too scientific. But the bigger the delta is between the cold air coming out of the supply into the servers or out of the servers back to the cooling system, the bigger the delta is between those temperatures, the more likelihood that there's something undesirable or something leading to inefficiencies going on within your data center. And so the idea is you want to be able to eliminate that, not only to increase efficiency, but to be able to increase your predictability of your cooling. So here's one example of a real data center that some folks at Rightline worked on. And what we see, the light green racks are racks that are operating, and I think the temperature was taken at mid-level. Those green racks are operating outside of ASHRAE's recommended range, right? So there's different ranges that you have now, but the green racks are outside the recommended range. So what this customer did was they used hot aisle containment in this case. And through hot aisle containment, they were able to get better performance, more uniform performance, and still be able to shut off 3 air handlers that were on the floor completely. And that's the magic between the heat containment. And here are basically just some of the numbers that backed up that last slide when they're being calculated. By shutting off the 3 air handling units, the CFM went down and the power drawn by those fans went down.